Okay, so hello everyone. So I am Subrata Samanta and I am a TA for the thermal physics course that is taken by Professor Devmalla Banerjee. So I am conducting this problem solving sessions every Saturday at 4 p.m. So this is the second session. Okay, so in the previous class I discussed the basic concept of Maxwell-Boltzmann distributions. Okay, and also solved some problems. Okay, assignment problems, and at the end I will discuss. I discussed some degree of freedoms of a different systems, but there are also some questions raised in the previous class. So I will discuss these questions first in these sessions, and then I will solve some problems, and after that I will discuss the concept of transport phenomena and the effusions and mean free paths. Okay, and the transport properties of the gases. Okay, so let's share my screen first. So if you have any questions, you can ask in the meantime, or you can ask now if you have any questions from the previous class, or any I mean from any of the lectures in the content week content. Okay, so let's first share the screen now. I hope my screen is visible. Okay, so I hope my screen is visible now, right? Okay, so in the previous class, at the end I will discuss I discussed uh, the degree of freedom of a diatomic and triatomic gas, right? So so let's continue with this. So let's say we have a diatomic gas, okay, H2. So let's say H2 gas, right? So this is basically a diatomic gas, two hydrogen atoms. Okay, yeah, if you have any questions. Okay, so let's say we have diatomic gas. So what is the degree of freedoms, okay, for this say H2 gas? Okay, so this is a diatomic gas. Right, so how many degrees of freedoms? So if we calculate the degree of freedom, let's at room temperatures. Okay, so at room temperature, let's say T around 300 Kelvin. So the H2 gas is a rigid molecules. Okay, so the degree of freedom is basically 3 translational degree of freedom plus how many rotation? 2 rotation, right? So there are 3 translations and 2 rotation. 2 rotational degree of freedom, total 5, right? But if you increase the temperatures, right? So after certain, let's say around T around 2000 Kelvin. So if you increase the temperatures, okay, and the temperatures let's say around 2000 Kelvin, okay, almost 10 times, okay, so then H2 gas, okay, try to diffuse, okay, then these gas molecules are vibrate, okay, so then we have to consider the vibrational degree of freedom as well. So if the temperature is around 2000 Kelvin, in this case, so there are 3 translational plus 2 rotational, and there is a one mode of vibrations, and each mode of vibration have 2 degree of freedoms. So 2 vibrational degree of freedom, right? So total 7 degree of freedom in this case, right? So if we plot, let's say I have plot the specific heat Cv with the temperatures. So once you know the degree of freedom, we can calculate the specific heat Cv. So this is basically F by 2, I think, kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically F by 2 kVt, right? So this is basically kb. Okay, so F by 2 kb. And we consider Avogadro number of particles, then F by 2 r. Okay. So this is basically for Avogadro number of particles in Na times Na. So this is basically F by 2 r. So for if you consider let's say very low temperatures, okay, so at very low temperatures, so this is the around room temperature. At very low temperatures, okay, let's say I have a divided by this, okay, so this is let's say around 300 Kelvin, okay, and this is around let's say 2010 times, okay, 2000 Kelvin, okay. So at very low temperatures we have only translational modes, the rotational modes is not active. So in this case your degree of freedoms only translations, translational. So 3r by 2, 3r by 2. So if you increase the temperatures, okay, around 300 kelvins, so the rotational modes are active, okay. So this is basically 5r by 2 a rotational, so there is a 5 degree of freedoms. Now if you increase the temperature further, so around 2000 kelvins, your vibrational degrees of modes are also active. So in this case the total your specific heat CV is basically 7r by 2, okay. So this is the plot, okay. So now you just draw a continuation line of this. So around this something like a plot, okay. So the CV versus temperatures of an H2 gas, okay. Okay, something like this. So this is for H2 gas, okay. So in this plot it's clear that so around high temperatures the vibrational modes, translations and rotational modes, all the modes are active, but at very low temperatures only translational mode are active, okay. So that's why your specific heat gives a 3r by 2, okay. So as the temperature increases the specific heat also increases, okay. And around 2000 kelvins the H2 gas diffusion starts, okay. So that's why the vibration modes are active and the specific heat increases, okay. So this is the I mean the questions that's raised in the previous class, okay. And for triatomic molecules, so this is H2. Now if you consider let's say H2O molecules, right, H2O molecules, this is a triatomic molecules. So for linear triatomic molecules, in the previous day I discussed that for linear triatomic molecule, linear triatomic molecules, okay. So let's say the system looks like this, okay. Let's say A, B, C and 3 linear molecules, okay. So in this case the total degrees of freedoms at room temperatures T around 300 kelvins, okay, the 7. So total degree of freedoms equals to 7. So 3 translation plus 2 rotational plus 2 vibrational, even if room temperature stay around 300 kelvins. So the total degree of freedom is 7, right. But if you consider H2 molecule, this is non-linear triatomic molecule. So this is basically example of non-linear triatomic molecule. Triatomic molecules. So in this case there are 3 rotational plus 3 translational, sorry, 3 in this case 3 rotational and 3 translations. So 3 rotational, 3 translational, okay. So total 6 plus 3 vibrational. If we include the vibrational degree of freedoms at very high temperature, so there are 3 total vibrational modes. So total total degree of freedom is 9, okay, at very high temperatures, okay. So total 9 degree of freedom, okay, at very high temperature if we consider the vibrational degrees of modes, otherwise there is total 6 degree of freedom, okay. And in this case if we consider only translation and rotational, then 5, okay. So this is basically total 6 if we only consider rotational and vibrational, sorry, rotational and translations, in this case 5 if we consider only translation and rotation, okay, if we neglect the vibration. So and we include the vibrational, so your linear titanium molecules the 7, okay, and in this case 9, okay. So this is the questions that's also in the previous class. So now today I will discuss, okay, so far any questions? Okay, if not, then I will discuss very basic concept of let's say first discuss very basic concept of Maxwell-Boltzmann distributions, and then I will discuss some molecular flux and the effusion process, okay. So the Maxwell-Boltzmann distributions, so in the Maxwell-Boltzmann distributions we consider, first of all we consider the monatomic gas, okay. So since we consider the monatomic gas, so there is only translational degree of freedoms are allowed, because only translational motions are possible, right. So if you consider, let's say Maxwell Boltzmann distributions, so in this case we consider the monatomic gas, so consider monatomic gas such that the only translational motions is possible, no rotational, no vibrational, okay. Since this is a monatomic gas, only translational motion, okay. So only translational motion possible. So what is the kinetic energy for this system, for this gas, okay? So then we can write the kinetic energy, the energy, basically the kinetic energy, because there is no potential, no interactions between the molecules, and we consider only uh, translational motions, okay. So the kinetic energy is very simple, so it's just like a half m, if the mass of the gas molecule is m, half m vx square and half m vy square and half m vz square, okay. So there is 3 directions, 3 translational, and the velocity in the x and y and z directions are vx, vy and vz. So you can write this is basically half m this v square. So v is the molecular speed and vx, vy, vz are the molecular velocity in the x directions, y directions, z directions, okay. So this is crucial. So this is the speed, okay. So this is the molecular speed, right, and these are the molecular velocities in the x, y and z directions, right. So velocity basically have vector quantities and v is the speed, is a scalar quantity. So v is basically square root of vx square, just like your r is square root of x square plus y square plus z square. So in the velocity space v, your speed is vx square, vy square and vz square. So now what is the distributions of vx, not v, okay. So what is the distributions of the questions, what is the molecular distributions so molecular distribution is the probability distributions with velocity, sorry, with velocity Vx to Vx plus dVx. Right? So here I am considering Vx, not V. Okay, so is the velocity Vx to Vx plus dVx. What is the distributions of this? Yeah, what is the distributions of the molecules? Okay, so this is basically f of Vx, some constant a times e to the power minus m Vx square over kVt. Okay, if we consider a thermal, bath at temperature T, okay, and the velocity is Vx for every molecules. Okay, so then the molecular distributions with velocity Vx to Vx plus dx is exponentially minus m Vx square by kVt. Now, if you want to compute Vx average, okay, what is the average velocities of Vx and how to compute? And what do we expect that the average velocity of Vx should be? First of all, it's 0 or it gives a non-zero, right? Because this is exponential functions and this is a symmetric functions. Okay, and your Vx can be both positive and negative because this is a velocity, not a speed. Okay, so if we compute the Vx average, so it's basically the range is minus infinity to infinity. So this limit is important when you compute the average of Vx. Okay, so this limit is minus infinity to infinity because Vx is velocity, and this is basically a times e to the power minus m Vx square kVt. Okay, so this is your f of Vx times Vx and d of Vx. Okay. So this is an odd functions and this is an even functions. Okay. If we expand the exponential, is basically 1 plus x square factorial 2. Okay. So this is basically 1 minus m Vx square over 2 kVt plus yeah, so basically 1, yeah, so plus m Vx square over kVt square over 2 factorials plus dot dot. Okay. So every terms is basically odd power of Vx, sorry, even power of Vx, right? So this is Vx square, Vx4, Vx6, Vx8. So that all are the even functions. Okay, and this is an odd functions. So if we integrate minus infinity to infinity, it gives 0. Okay. Right. So similarly, if we compute f of Vy, so basically a times e to the power minus, so it's m Vy square over kVt. Okay. Again, if you compute Vy average, it gives 0. Okay. And similarly for z, f of Vz a e to the power minus m Vz square over kVt, and if you compute Vz average, it gives 0. So individually they all gives 0. Okay, but so what is the now I want to calculate the speed distributions. Okay, so these are the velocity distributions. Now I want to calculate the speed distributions. So speed distribution is basically f of, okay, so first of all, if we want to compute Vx and Vy average, so not Vx average, not Vy average, but then their product, and we take a average. Okay. So what is the average values of Vx and Vy? Okay, so how do I compute? Because in the Vx Vy average, if you want to compute, that basically minus infinity to infinity Vx Vy and your f of Vx and f of Vy, you just multiply. Okay. And this is basically dVx and dVy, right? So this is also 0. because your Vx and Vy are independent. Okay, so this is basically minus infinity to infinity Vx f of Vx dx and minus infinity to infinity. So basically there is a two integral, so there is a two limits. Okay, and minus infinity to infinity Vy f of Vy dvy. Okay. So both are separately 0, so it gives 0. But if you compute Vx square average, so how to compute? The same way, so minus infinity to infinity Vx square. So first of all, so I take Vx and Vy are different, right? So Vx and Vy and take their average. But now I want to compute the Vx square average. That means Vy now Vx, okay, and then I calculate the average values of Vx square. So that gives it's a non-zero value. So minus m Vx square over kbt, okay, and then dvx. So now this is an even function and this is also an even function. Okay, so that gives a non-zero value. Okay. So that means your Vx Vy, okay, so it gives 0 because Vx and Vy are not correlated, they are independent. Okay. But when you consider Vx and Vx, so this is basically Vx times Vx and their average. So they are both same. Okay. They are not independent. That's why it gives a non-zero value. But in this case, so Vx and Vy are independent. Okay. That's why when you take a when you take a average of their product, okay, it gives 0. But in this case, it's non-zero because they are same. Okay. So that is so now, so for this case, so that's Vx and Vy are, now we know that the Vx and Vy are independent. Similarly, because the f of Vx and f of Vy are independent. Okay. So your molecular speed distributions, now if you from the speed distributions f of V, that means your molecular speed now V to V plus dV, not a velocity. Okay. So in this case, f of V dV is basically f of Vx, f of Vy, f of Vz, and then we have a quantity that dVx, dVy, dVz, right? But when we consider this, there is a 4 pi V square dV. This is a volume factor. Okay, 4 pi V square dV. Because if you consider a sphere, okay, and that is the volume factor. Okay, so 4 pi V square dV. This is basically d cube V. Okay, so this is not a dV, it's a d cube. And d cube V gives us 4 pi V square dV, and there is a normalization factor A. So basically this is just like a e to the power minus m over kbt Vx square, Vy square, Vz square exponentially at and then 4 pi V square dV. Okay. So this is basically a e to the power minus m over kbt V square, okay, then 4 pi V square dV. So this is your speed distributions f of V d cube V. Okay. So this is the volume factor d cube V. Okay. So there is a, by convention there is a half factors in this case. So I write, let's say, m over 2 kbt. Okay. So from the beginnings I write, let's say, 2 kbt. Okay. So 2 kbt. because half m v square is E by kBt, so by conventions I put a 2, okay, everywhere. So when we multiply these things, your f of v is just multiply of f of vx, vy, vz times v square. So this is only true for isotopic case. So this is only true for isotopic case. So we consider the isotopic case, isotopic distributions. So in each and every directions the velocity distributions are same. So that's why when you consider the speed distribution, we just multiply it with it along these three directions. Okay, f of vx, x directions, f of vy, y directions, and f of vz are z directions. Okay? Because the distributions are isotopic. Okay. So now okay, I hope am I audible, right? Okay, so now I want to compute the V average. So now if you want to know the things that what is your f of V dV, d cube V, this is basically a times v square e to the power minus alpha v square dV. Okay. Now if you compute V average, okay, now if you compute the V average, that gives a non-zero value, right? Because here is the limit. So basically if you compute V average is minus, not minus infinity, 0 to infinity. So the V is limit is changes, so is 0 to infinity because now V is a molecular speed. This a times v square e to the power minus alpha v square times v dV. Okay, this is basically 0 to infinity a v cube e to the power minus alpha v square dV. Okay, it's still there because the limit is 0 to infinity, so it gives a non-zero value. Okay, okay, so that's now if you compute 1 over V average. Okay, let's say I compute 1 over V average. So just for completeness, it gives you, so if you include the normalization factors, okay, a, so it's basically 8 kBt over pi m, 8 kBt over pi m. Okay, so have the alpha value. Okay, so I give the values of alpha and a, right? So the values of a is yeah, so the values of a is m over 2 kBt 3 by 2, okay, times 4 over square root of pi, and alpha is m over 2 kBt. Okay, so now if you compute 1 over V average, okay, what is the values of 1 over V average? This is not equals to, first of all I telling you that this is not equals to 1 by 1 over V average. Okay, we will check. So if you compute 1 over V average, so this gives 0 to infinity 1 over V times a times v square times e to the power minus alpha v square dV. Okay, right. and that is so basically this is 0 to infinity a times v e to the power minus alpha v square d. So clearly you see that this is not just 1 by v average, so this is not equals to 1 over v average, right? So if you calculate this, so this is a homework. So if you calculate this, the v average times 1 over v average, okay, so it gives the 4 over pi, okay. So the v average times 1 over v average, it gives a 4 over pi, okay, it's not 1, okay. So in this line, so this is basically a over b, the expectations values of a over b, okay, is not equals to the expectations values of a or the average values of a over average values of b. Right? So this is also true that basically v times, so it's basically v times 1 over v minus v average and 1 over v average, that gives a non-zero, right? So because v and 1 over, so this is basically 1, so the first term is basically 1s, okay, 1 and minus this is just calculate 4 over pi, okay, so this is non-zero, right? So if you want to calculate this quantity, that v times 1 over v minus v average times 1 over v average, so this gives a non-zero, okay. So there is also one problem in the assignment. So calculate the mass RMS speed of nitrogen molecules at room temperature, okay. So calculate the RMS speed of nitrogen molecule at room temperatures, okay. So basically T is 300 Kelvin, okay, around 300 Kelvin. So you know that what is the formula of VRMS is square root of three RT over m by m, okay, and we know what is the values of m n2, okay, so it's basically 28 gram, and if you know the values of r, okay, so just plug into this, so the result is basically 500 times meter per second, okay. So sorry, 3RT by m, not pi m, 3RT by m, the RMS speed, right? So the RMS speed is 3RT by m. Yeah, so 3RT by m is the RMS speed. And there is also another problem that let's say the average for a monatomic gas. So for a monatomic gas, So the kinetic energy, the average kinetic energy is basically 3 by 2 kBT. The average energy, average kinetic energy is 3 over 2 kBT. Okay, that is given, let's say 10 to the power minus 15 joule. Okay. Now aim to calculate the number density, okay, at pressures 1 atm. Okay. So calculate number density N at pressure P equals to 1 atm. So at pressure P equals to 1 atm, we want to calculate the number density N. Okay. So how to calculate? So first of all, I think you know that why the average energy is 3 over 2 kBT, because there are 3 degrees of freedoms for a monatomic gas transformation. So, okay. So from this we calculate the temperature T, right? You calculate the temperatures from these equations, okay, because the average values of energy is given 10 to the power minus 15 joule. And to calculate the temperatures, okay. So now once you know the temperatures, so this is basically PV equals to N kBT, right? And your N, the number density, so the number density small n equals to N by V. So this is basically P over kBT. Okay. So kBT, from this we want to know that what is the values of kBT. Okay. And we know the pressure at 1 atm. Okay. So just plug into the value, we get a number density. Okay. So now I am going to discuss the concept of solid angle. Okay. That is very interesting part. Okay. And that uses in many places. Okay. So the solid angle. Okay. So let's consider first a 2D circle. Okay. And the radius of the circle is r, and let's consider an arc. Okay. So this is basically an arc. Okay. This is basically theta angle. Okay. So what is the length of this arc? Okay. So what is the length of this arc? The S, the length of the arc is basically r times theta, right? It is angle theta with the center. So this is a center O. Right. And what is the values of circumference? Now if you know the circumference S equals to, let's say, 2 pi r, okay, for circumference. Then the theta is basically, so then the theta values is basically 2 pi. Right. So first I calculate the length of the arc is S is equals to r times theta. Right. Now we know that the circumference of a circle is 2 pi r. So then the values of theta is basically 2 pi. So I do the similar thing for a 3D, okay, for a 3D object. So basically, if you consider a volume element in 3D, so this is basically area length. Now you consider an area in 3D. Okay. So let's first draw this thing. So let's first consider an area element on a, let's say, sphere. Okay. So here I consider circle, now I consider a sphere. Okay. And let's say this is the so this is your let's say x-axis, y and z. This is the phi, and this one is d phi. Okay. And if we consider an, so in this case there is also this kind of curve. So this is your selected area on the sphere, on the surface of the sphere. So it's basically the length at from the origin, right? So this is your area dA on the surface, and this is basically from the origin the r distance. Okay, because this is a sphere and I consider a very small element, okay, dA on the surface of the sphere, that is basically at r, and the radius of the sphere is r. Okay. Now in this case, what is the solid angle? So here is the angle, means that the angle in the plane, but in this case we are calling this a solid angle, okay, because this is 3D object. So this area element dA, okay, so this area element dA what is the angle, okay, that this area element dA created at the origin. So this is basically the angle is that, so 3D object, okay, with a 2D angle. Okay, this is a solid angle. So in order to calculate the solid angle, d omega, so first calculate, write down the area of this small element dA on the surface. So what is the area of this small element dA? So it's basically r, and this is an angle theta. So this is the theta. So this is the theta. So then the area element is basically r times cos theta, r cos theta, sorry, r cos theta. So r sin theta d phi. So this is r cos theta in these directions, but in these directions r sin theta. So r sin theta d phi times r d theta. Right. So basically the length in these directions and the length in these directions, right? Okay, let's zoom into this. So it's basically I have a this kind of area. Okay, the length of this is r sin theta d phi, and the length of this is r d theta. R d theta, and this is r sin theta d phi. Okay. So therefore the area is just multiply r d theta times r sin theta d phi. This gives you r square sin theta d theta d phi. So then the solid angle, similarly as in before, that d omega, okay, so this is a solid angle, is basically dA over r square. So in this case, it's basically theta is your 2 pi r over r, it gives a 2 pi. So in this case, the d omega is dA for a small element. So here I am saying that the theta for a whole circumference, but here for a small element dA, the d omega is dA over r square, which gives you sin theta d theta d phi. Okay. Now you compute the total solid angle. So this is a differential solid angle. Okay. So now if you calculate the omega, the total solid angle, you have to integrate. So the theta limit is basically 0 to pi sin theta d theta times 0 to 2 pi 0 to 2 pi times d phi, right? So this gives you that 2 times 2 pi, right? So this gives you 4 pi. So therefore the total solid angle, okay, it's a 4 pi, and for a small element area dA, the solid angle is sin theta d theta d phi, that is d omega. Okay. And for circles, this is a total solid angle, I mean in this case angle is 2 pi, and for 3D objects it's basically solid angle, and total solid angle is 4 pi. Okay, so let's consider the similar things. Let's do on examples. Let's consider a sphere. Okay, and we consider a thin strip on the sphere. Okay, so this is basically thin strip on the sphere. Right. So now I want to calculate this thin strip. What is the angle that this thin strip makes with the origins? Okay. So basically, if you consider the point of these two line, okay, d theta and at angle theta, and they take all values of phi, right? So in the previous case we consider only a element, but in this case I consider a strip. Okay, there is only one variable, theta it changes, phi is basically take all values. Okay, and in this case we have to fix both theta and phi. In order to calculate these things, so this, let's say this is a perpendicular directions, okay, and then this is z directions. Okay. So in this case if you want to calculate the d omega, so I know what is the values of d omega in this case, it's just sin theta d theta d phi, sin theta d theta, but in this case d phi it takes all values. Okay, so that's why you have to integrate 0 to 2 pi d phi, so that gives you 2 pi sin theta d theta. Okay. So these thin strips, okay, makes a solid angle d omega, that is 2 pi sin theta d phi at the origins. Okay. Okay, so that is the concept of solid angles. Now I'm okay, so let's do one more thing because that is something related. So okay, I mean so if you know that what is the values of speed, so let's consider the molecular flux. Okay, so now I will discuss the molecular flux. Okay. So molecular flux and related problems. So in the molecular flux, so first of all, what is the flux? Just a brief review that The flux is basically the number of molecules over number of area per time. Okay, and that is basically if you denote the flux phi. Okay, so I am not going to the derivation, just 1 over 4 times n times v average. Okay, where n is the number density and this is the average velocity. Okay, sorry, average speed. Okay, so here v is the speed. And if you follow the ideal gas, I mean the Maxwell-Boltzmann distributions of a monatomic gas, then we know that what is the value values of this and V average. Okay, so for MB distributions, if we follow the MB distributions, the Maxwell-Boltzmann MB distributions and ideal gas. So in this case, the V average so 8 kBT over pi, right? And the flux phi is 1 over 4 n okay. Okay, so now what is the n? N is the number density, right? So you know that how the number density n is related to the pressure. So pressure P equals to n kBT. Right? From this, the values of n is basically P over kBT. So this is ideal gas law, right? PV equals to nRT. So use this basically on the flux phi is P over log of 2 pi m kBT. So that means your flux phi is proportional to P over square root of T. Because other things are constant. Okay, if the mass is constant, okay, and kb is a Boltzmann constant, so they vary proportional to the pressure and inversely proportional to, sorry, 1 over square root over T. Okay, and if we change the mass, then it's a phi is also proportional to 1 over square root of m. Okay, so now I will discuss the concept of mean free path. Okay. So basically, so in this case, you make a own problem. So let's say we have a temperature T1 and T2. The T1 is greater than T2. Right? Let's say the T1 is 2T2. Okay, how the flux changes? Okay, where the P, M are constant. Okay, so then the flux phi 1 over phi 2 is basically square root of T2 over T1. This is basically square root of T. So the flux phi 1 square root of T phi 2. Right. So this kind of problems. Okay, so how they vary with temperatures, how they vary with pressure, how they vary with mass. So once you know this, you can easily compute this kind of problems. So now I will discuss the mean free path. Okay, so what is the mean free path? So the mean free path is basically, so first consider a intermolecular separations. Okay, D, let's say intermolecular separation. So intermolecular separation means that, let's say consider a container, okay, and there is a partition. So in the left side the temperature T1 and pressure P1, in the right side the temperature T2, pressure P2, and there is a small hole. Let's say there is a small hole at the heat this side gas molecule hit this wall and passes through the hole, and this side gas molecule hit through the wall and passes through the hole, right? And I denoted that this small hole with diameter let's say D. Okay. So now there is a two scenario where this D is very greater than lambda. So where lambda is the mean free path, and second is D is very less than lambda, where lambda is the mean free. So now I consider the first situations. So where second situation, case 2, where D is very less than lambda. So that means, so in this case this is basically an effusion process. Okay. Your mean free path is larger than your so larger than the diameter of this hole. Okay. So that means the gas molecules are basically effused. So effusion process. So this is basically an effusion process. Effusion process, where the flux balance to get a equilibrium situations, right? The flux it changes, okay, because the gas molecule passes through the holes, okay, the flux it changes. So this flux balance to get a equilibrium situations. So how to reach a equilibrium situation in this scenario? So we are, in order to do that, we have to balance the flux. Okay, so this flux already I discussed here, okay, before. Okay, so this is the flux, the molecular flux. Okay. So number of molecules per area per time. So if we calculate this, okay, so let's say okay, so so this is a mean free path, and now I'm considering the mean free time. So mean collisions time and mean collision time tau. This is basically 1 over n sigma v. Okay. So this is basically, now what is the mean collision time? So you know what is the mean free path. Now you know what is the mean collision time. So the mean collision time is basically the average time elapsed between the collisions. Elapsed. Okay, so elapsed between the collision. So what is the average time between the collisions? And the sigma is the, this is average, and the sigma is the collider is the collision cross sections of the molecules. Okay, so it's the collision cross section, okay, of molecules. So what is the collision cross sections? If you know the collision cross section sigma, okay, and if you know the number density n and is the velocity v, so you can calculate the mean collisions time. So how to calculate the collision cross sections? Because this is something like pi d square, where d is the diameter, okay, of the hole. Okay, so yes, so now, so let's do one exercise. Okay, so exercise 1, then it become more clear. Calculate the mean free path for a gas of nitrogen. Calculate the mean free path for a gas of nitrogen in, okay, at room temperature. By the d at the diameter of the molecules is given, diameter, so d is given, so 0.37 nanometer. Okay, so how to compare? So what is the formula of the mean free path? We use the formula of the mean free path, lambda, basically 1 over square root of 2, okay, n pi n sigma. So what is the sigma? Sigma is basically pi d square. So 1 over square root of 2 n pi d square. Now how to compute the n? Number density. Okay, so since the T is equal to 3 Kelvin, also I use the standard pressure, P is 1 atm. Okay, I use, so also is given. Okay, so this is basically 10 to the power 5 Pascal. So let's say pressure at 1 atm. Okay, then we can calculate n. So it's P equals to n kBT, and n is 10 to the power 5 Pascal over kBT is 300 Kelvin times the temperature 300 Kelvin, and kb is 1.38 times 10 to the power minus 23, right? So this gives you 10 to the power 25 per meter cube, right? And we know that what is the values of d is 0.37 nanometer. So plugging these values into these expressions, okay, so we get that lambda around 6.8 times 10 to the power minus 8 meter. Okay, so this is your mean free path. Okay, so we just check that one. So 10 to the power 25 n and d is nanometer. Yeah, so just check the order of ordering. So 10 to the power n is 10 to the power 25, and sigma is d square. So d square is 0.37 times 10 to the power minus 9 meter and square. So it's basically, let's say 10, and so it's around 10 to the power 20 minus 1, right? 10 to the power minus 21. Yeah, so this 9 and 80, 20 minus 90. So 10 to the power minus 18 times 10 to the power minus times 10. right? So this is basically 3.7 and 3.7 square, so it's around, let's say, 10. Okay, and so I'm just taking order, now I'm ordering. Okay, so yeah, 10 to the power 8. Yeah, so this is 10 to the power minus 90, of the order of 10 to the power minus 19, and your n is order of 10 to the power 25. So basically your lambda is 1 over square root of 10 to the power 25 minus 19 times a factor, so it's 10 to the power 6, and then if you include the other factors, it's 10 to the power minus 8. Yeah, it's correct. So it's the order of 10 to the power minus 8. I think this lambda is basically 0.68 nanometers. Sorry, 0.68, 0.068. So 0.68. So 68 times 68 times 10 to the power minus 8 times 10 to the power minus 1, right? So it's basically 68 nanometer. So this is your min frame. Okay, so and for the other regions, so this is the case where the d is very less than lambda. So this is the effusion process. Okay? And the other case 1, where your d is very greater than lambda. So in this case, how to balance the pressure? So the equilibrium, so in the diffusion process, so this is basically a diffusion process, a diffusion region, diffusion region. So in the effusion process, where the d is very less than lambda, to reach a equilibrium systems, okay, we balance the fluxes, right? A diffusion process, how do we reach an equilibrium system? So in this case, the equilibrium, that means the pressure P1 equals to P2. So balancing the pressures. To reach equilibrium, we need to balance the pressures. Balancing the pressure. Okay, so these are two important things. Okay, so far any questions? Okay, so if not, then I will discuss the transport property of gases. So transport properties of gas. Okay. So what is the transport property of gas? So far we discussed the dynamics of the gases, right, in equilibrium. basically the in equilibrium how the gas molecule, or what is the probability distributions of the gas molecule, that is the Maxwell-Boltzmann distributions. And yeah, so the effusion process, diffusion process. But now I will discuss the viscosity, that is the transport of momenta, okay, thermal conductivity, that is the transport of heat, okay, and the diffusion, the transport of particles, right. So far we discussed the dynamics of gases in equilibriums. Now I will discuss the viscosity, this is basically the transport of momenta. Do the thermal conductivity, that is the transport of heat, okay. So there is a question that how to just a minute. Yeah, how to calculate the collision cross sections of the molecules. Yes, so okay, so let's discuss this thing. So I will change this. Okay, I'll come back to this point. So let's draw an picture. Okay, so let's say we have a two molecules. Let's draw an pictures. Okay, so this is okay. So there is a several molecules. Okay, so let's say each molecules, let's say consider the molecules air, air, air. Okay, so these are the molecules. Okay. So when the two molecules are collide, okay, let's say this molecule and these molecules, so there are two different molecules are collide in this position. So same one, right. And we know what is the radius of the molecules, we know. So each molecules have their own volumes, own radius. Okay, in every cases. So there is a molecule, there is a molecules, and each molecules have radius, let's say a1. Okay. So this is, let's say, 2a1. Okay, so each molecules have radius a1. So what is the distance? If the radius of the molecules, let's say a1, so what is the distance? Is 2a1, right. Right. So now the collision cross sections of molecules sigma, collision cross section of molecules. So how to calculate? So we consider a scenario where two molecules are collide, just collide, and their intermolecular separations is now 2a. Okay, because each molecules has radius a1, 2a1. Okay. So what is the cross sections for this case? This is basically pi times 2a1 square. So now I consider a, so this is basically a diameter of a effective molecules. How do I draw? Let's see. So this is basically, so this is the effective area. Okay, so this is your effective area, and the collision cross sections is the area of this. So this is basically pi times, what is the diameter of this green circle? So this is the, what is the area of this circle with diameter is 2a1. So this is the area is pi 2a1 square. So this is gives a pi d square, but d is the diameter of the molecule. Now you see that this is d is basically a1 to a1. So this is basically your diameter of the molecule, diameter of the every molecules. Okay, so now it's clear. Okay, so Vinodini asks this question, so now it's clear. Okay, so now I come back to this point. Okay, so the transport property of gases. Okay, so viscosity, that is the transport of momenta, and the thermal conductivity, the transport of heat. Okay, and 3 is the diffusion. Okay, so diffusion is a transport property. Okay, here I am considering the flux and mean free path. That are the flux balance to get equilibrium situation. These are not transport properties, but the diffusions. So this is an effusion process. But in the case where d is very greater than lambda, mean free path. Okay, so then the particle transfer from one side to another side. So we need to balance the pressures in order to reach equilibrium. So this is basically a transport property. Okay, so the diffusion is a transport of particles. Transport of particles. Okay. So this is basically understood in this way. Let's so this is this. Let's first copy this. Such that copy. Okay. Okay, good. So now I consider a fluid. Let's first consider the viscosity. Okay. So first is viscosity. So I consider a fluid. Let's say So this is a tube, and fluid is flowing like this. So the fluid is flowing. So this is a basically, so upper side of the tube. So the there is a velocity gradient. So basically there is a velocity gradient. So that means this is moving and this is moving in opposite directions. Okay, because the both ends are moving in opposite directions, that's why they creates a velocity gradients in the fluid. Okay, so the velocity gradient is basically they are the these are the velocity. Okay, these are the velocity gradient. So flux, sorry, not flux, the shear stress, okay, shear stress between the layer. Okay, so this is the layer. So these are the layer 1 and this is the layer 2. Okay. So the between the layers, so the shear stress between the layers, okay, is proportional to the velocity gradient that is perpendicular to these layers. Okay, so the shear stress between the layers is proportional to the velocity gradient. So we consider a small layer, let's say this one, this one. Okay, so this is the one layer and this is the second layers. Okay, and the shear stress between the layers is proportional to the velocity gradients. Okay, and that is perpendicular to these layers. Okay, is perpendicular to this layer. Okay, so that proportionality constant is called the viscosity. So this proportionality constants, so this is a proportional, and the proportionality constant is called the coefficient of viscosity. Coefficient of viscosity. Eta. So what is the values of eta? So eta is 1/3 m n lambda v average. So where lambda is the mean free path, is basically 1/square root of 2, right, n pi d square. Okay, the d is the diameter, and here if we just plug into this, so this is basically 1/3 molecular mass. Number density I just replace with number density times lambda, I replace with v average times root 2 pi d square, right, because n times lambda is 1/root 2 pi d square. So this eta is basically independent of pressure. So that is the interesting. So the coefficient of viscosity eta is independent of pressure. There is a no n number density. We just discussed that if there is a number density, that basically depends on pressure. Okay, but the number density is cancelled. Okay. So you can eliminate the number density. So that means this is an independent of pressure. Independent of pressure. Okay, but it's proportional to the temperatures, not proportional to the directly proportional to the temperature, square root of temperature, because the v average So the coefficient of viscosity, okay, so the coefficient of viscosity eta is proportional to the velocity average, sorry, the speed, the average values of speed, okay, molecular speed, not velocity. So that is basically proportional to square root of t, okay? Because we know that the average values of speed is basically proportional to the square root of t, and eta is proportional to m over d square. Okay? So it's linear proportional to the m and inversely proportional to the 1 over d square. So these are the importance when you solve some problem. So how the viscosity changes with temperature, changes with mass, changes with diameter of the molecules. Okay. Okay, let's do an on examples. So for N2 gas, again I choose an N2 gas as an example. So for N2 gas at T equals to 300 kelvins and pressure, let's say 1 atm, and we know what is the values of m N2 is 28. If we say atomic unit is U, so 1 U is 1 U atomic unit, so it's basically 1 over Na gram, okay. And Na is the Avogadro number, and the diameter is again for N2 gas is given is 0.37 nanometer, okay. And if we calculate the V average is basically 8 kBt over pi m. So here I write m, okay. So this is basically, it's not the total mass, it's the molecular mass, okay, m. And capital M, if we write a capital M, this is basically total mass, okay, m times Na, okay. So capital M is basically small m times n, Avogadro number, but small n is a molecular mass. So eta is 1 over 3 small m times n, or I can use this formula, there is a no n, so it's V average over root 2 pi t square. So you know everything. So, okay, so V average you know because the temperature is given. Okay. Pressure is not needed. Okay. Right. Or in other words, if we given the density, then we can calculate the velocity average. Okay. And then we also calculate the viscosity. So let's say the second example, again for let's say N2 molecules. Okay, given the density for N2 molecule, okay, the density is given. So given the density, let's say eta or rho, sorry, eta is a coefficient of viscosity. So given the density is rho, is let's say 0.023 kg per meter square. Okay, that is the density, right? And the average speed is given, let's say 500 meter per second, and the coefficient of viscosity also given, eta it's 83 10 to the power minus 5, okay, Newton second meter to the power minus 2, okay. So Newton second meter to the power minus 2. So now I want to calculate the mean free path. So calculate lambda, that is the question. So how to calculate lambda? Okay, so let's write down the formula of eta. Let's see all the parameters are given or not. So 1 over 3 m n lambda in PFH, right? That is the formula. And I want to calculate lambda. This is basically 3 eta over a min times V average. What is a min? Right? Because there is a nowhere the n is not given. Right? M we know, let's say m is not given, n is not given. Okay. So what is the m? So but the density is given, right? So if you write down the density rho, what is the density? It's m by v, right? So this is a mass density, right? The total mass over volume. Now in this case, I wrote the capital M, right? So this capital M is basically small a, sorry, n times small m divided by v. So now small n, sorry, capital M over v is basically small n times m, right? So this is basically your density. So 3 eta over rho v average. So where rho is, okay. So this density is the rho is the mass density, and that is basically m by v, and we can just write m in terms of n. So you can easily calculate, because all the parameters are given in the right hand side, eta, rho and v average. You just calculate lambda. Okay. Okay, so far any questions? Okay, if you have any questions, you can also write in the chat box. Okay. Okay, so if not, then I will quickly discuss about the next one is the thermal conductivity, and I will skip the diffusions, because if, let's see, in the next class maybe I will discuss the diffusions, but not today. So today I will discuss the thermal conductivity parts, okay, and solve some problem related to this. Okay, so far any questions? Okay, so it seems that there are no questions, so I will continue. Okay. So thermal conductivity. Thermal conductivity. So what is the thermal conductivity? Okay, so here what I wrote is the transport of heat. So the viscosity of the transport of momentum is basically the velocity gradient, and thermal conductivity is the transport of heat. So how much amount of heat flow along a temperature gradient? How much amount of heat flows along temperature gradient, right? which is depends on the thermal conductivity of the materials. So which depends on the thermal conductivity of the materials. Okay. So in 3D, so what is the heat flux? So in 3D, the heat flux basically J vectors is minus kappa times gradient of temperature. So this is a temperature gradient, is a vector quantity, and this is also right side is a vector quantity, left side. Okay, the heat flux, okay, in 3D. So this is basically in 3D, in 3D, and that is the temperature gradient, and this is a kappa. Okay, that is thermal conductivity. Okay, thermal conductivity kappa. Right? Now what is the formula of kappa? So kappa is basically 1/3 Cv times lambda and V. Okay. So where Cv is the heat capacity per unit volume. Okay, so this is important. Here the Cv is the heat capacity per unit volume. Okay. So now this is also a independent of process. How do I say? So what is the expressions of Cv? So Cv again is depends on n, right? Because your lambda is depends on n, number density of the pressure, right? Because if you write down the lambda, basically 1/√2 n by t square. But the Cv is also depends on n. Okay, just write down the heat capacity per unit volume. This Cv is basically n by V. Okay, this is C mole. Okay. So what is C mole? The heat capacity of a single molecule. This is the heat capacity of a single molecule. The heat capacity of a single molecule, okay, times n, that means the heat capacity of a total n molecules, divided by V, that means the heat capacity per unit volume. That is the Cv. So therefore Cv, the heat capacity per unit volume, which is basically small n, this n by V. Okay, so this n by V, small n times C mole, the heat capacity of a single molecule. We plug into this here, so this 1/3 times n times C mole, the heat capacity of a single molecule, times lambda 1/√2 n over pi d square, and again V average in the numerator. So this n cancel. So this is again the kappa is also independent of pressure. Okay. Kappa is also independent of pressure, and this kappa's proportionality is important. So this kappa is proportional to, again, the V average is proportional to square root of temperatures, because the V average is proportional to square root of temperature. Okay. And also kappa is proportional to 1 over d square, okay, and is proportional to C mole. So basically, let's say we have a temperature T1. This is the example. Then let's say temperature T1, your thermal conductivity is kappa 1. At temperature T2, your thermal conductivity is kappa 2. Okay. And let's given that T1 it's 42. Okay. So then what is the values of kappa 2 by kappa 1? What is the values of kappa 2 by kappa 1? So basically kappa 1 over kappa 2 square is basically T1 over T2, right? Because kappa is proportional to square root of T, so kappa 1 square. This is basically 4. So that means kappa 1 is 2 kappa 2. The ratio is kappa 2 over kappa 1 is half. Right. In the same way, if there is a two diameters, okay, T1 and D2, then we can also calculate the ratio of kappa 2 kappa 1s, okay, because we know how this kappa vary with diameter D, while the other fixed, okay, the temperature, average velocities, sorry, average speed, okay, and C mole is fixed. Okay. So just a quick question, let's say at temperature T, the number density, let's say N. Okay. So just for understanding that, let's say kappa is 1 over 3 Cv times lambda and this V average. So now at T, so kappa is number density N with number density is equals to N. Okay. Now if we change the number density N to 2N, how the kappa changes? How the kappa changes? So kappa goes to, let's say, kappa prime. What is the velocity? So think about it. Okay. I think I will discuss already this thing, but just a understanding. Okay, just for understanding. Okay, so if you have any questions, you can ask. Okay.